Brobdingnag, the land of the giants. Every object seems out of scale with mere human dimensions. The LEP tunnel itself, so that is the large electron positron collider ring, for example, it's 26 kilometers long. It's wide enough inside to easily accommodate a modern sport utility vehicle or two, should it ever be turned into an underground racetrack. The tunnel is accessible from the surface at one of four different laboratory locations. At each site, one of four mammoth particle detectors can be found. Each is the size of an apartment building built deep below ground, contained in experimental halls that could dwarf the stage at Radio City. Each behemoth is constructed from thousands of separate components fabricated by hundreds of physicists and technicians hailing from dozens of countries scattered across the globe, and each is built to a precision of fractions of a millimeter. The MIT physicist Vicky Weisskampf dubbed such devices the Gothic cathedrals of the 20th century. From the start of construction to the completion of the first experiment, a decade can easily pass. This is in sharp contrast to the timescale of the processes being investigated, which occur in less than a billionth of a second. Such experiments repeatedly recreate and measure for a fraction of a second the conditions and interactions of matter and energy, including, as we shall see, the extremely rare events which may have been last experienced in our universe 10 billion years ago. The LEP collider imparted energies to elementary particles that were far beyond those produced anywhere else in our galaxy, except perhaps in the shock wave from an exploding star, or in the final collapse of a gigantic black hole. Charged particles were accelerated by electric and magnetic fields around the tunnel so that they traversed the Swiss-French border without passports, near the airport, and then again at the base of the Jura Mountains 10,000 times each second. In the process, they achieved energies of almost 1 million times the energy they store at rest. Yet these gargantuan values are still 1 million times smaller than the average energy carried by every particle when the universe was the size of a baseball. The collisions between individual particles at that time were so energetic that to recreate them with present technology, one would have to build particle accelerators with a circumference bigger than the circumference of the moon's orbit around the Earth. So, quite a bit. It's difficult to build these things. The voyage from LEP to the primordial universe is more than a voyage back in time. It is a voyage in scale that helps take us and our atoms much of the way from Brobdingnag to Lilliput. As out of this world as the colossal detectors in the LEP experimental halls may seem, their mismatch to normal human scales is inconsequential compared to the degree to which the scales of activity in our current universe dwarf those that were relevant when atoms were conceived. The huge densities and temperatures at that time are reflected in an equally matched subatomic ferocity. Let us return to the barrage of atoms in a drop of water again, as seen under the microscope. The Brownian jumps. So remember we talked about Brownian motion. The Brownian jumps of a dust speck are produced by the collective collisions of billions of jiggling atoms in the water, each momentarily traveling at hundreds of kilometers an hour. But a single subatomic elementary particle in the primordial gas, when the universe was the size of a baseball, carried enough energy to, in a single collision, knock the same dust speck not only right out of the water, but out of the earth. If we try to ratchet up such a collision to a human scale, It would be like accelerating a rocket in space to such a high speed that upon colliding with the moon, it could kick it right out of the solar system.